The topic is finding nanoscale needles in a Peta-Scale haystack. Fancy title, huh? Okay. This is the actual title I came up with, but the more creative brains who were reviewing my slide deck said, change it, put it to that. Let me see if I can do the justice to the fancy title. So I'll start with introducing KLA Corporation, the products that we make. I'm not sure how many of you are familiar with it. KLA is not a very regular customer at supercomputing. Some trends and challenges, the kind of data rates and storage requirements that we are facing, 5 motivations for DDN, adopting DDN. I think the last point is kind of obvious. I don't think I need any slides for that, but let me see. Let's go ahead. So KLA Corporation is a 40-year-old company, 8 billion revenue recently, global company, high technology company. We have research and development. We put a lot of money into research and development also. We are in semiconductor industry. And all the chip manufacturers are our customers, like TSM, foundries like TSMC, memory manufacturers like Samsung, Hynix, they are all our customers. So what do? I mean, if you're familiar with semiconductor build process, then yeah, it's good. But if you're not familiar with it, basically what they do is they start with the silicon substrate. They have the reticles or masks using which they make layers upon layers, and they go through, for making a single chip, they go through roughly from multiple hundred to thousands of process steps, wherein they add material on top of material, they do etching, they cut the material out, they do various processes called lithography, multiple hundreds of steps to get to the final chip. So once they make the chip, they can put it to electrical testing, functional testing, and determine is the chip working or not. But in most cases, this hundreds of process takes about 5 to 6 months. So driving blindly for all that period without knowing what the final outcome is not good for them. So what they want is inline monitoring of their process steps. So as they add a material, they make a new layer. They need to make sure the surface of the material is the way it has to be. And once they etch, they need to see if there are any residues left during the etch process. And when they have multiple layers installed, they need to measure the thickness of each of the layers. Is it uniform throughout the die, throughout the layout of the die? They need to see the geometry of this layer. Once they etch and make pillars and columns of materials, they need to measure the thickness of the column on the top, at the bottom, in the middle, the height of the column. They have a lot of critical parameters that they need to measure as they move from one layer to another layer. And they need inline monitoring and constant feedback given to them such that the final product which they come to after 5 to 6 months is a functional product. And that's where KLA comes in. We have the flagship products that we make are these wafer inspection, reticle mask inspection devices, and also metrology and measuring devices. We measure various dimensions of all these things that they are talking about and give them real-time feedback. Those are the flagship products that KLA makes. Other than these flagship products, we also have many other divisions which work in printed circuit boards, flat panel displays and all. But I am in a division called broadband plasma division, and we make optical inspection and metrology products which measure all these various components that we're talking about. So the scale of this problem, the difficulty of this problem is we know the process dimensions that all the chip manufacturers are using these days are in below 10 nanometer scale. So that means the defects that we are measuring are also in that scale, 10 nanometer or less than 10 nanometer. If during the etch process there is something, a residue is left behind, then that residue that we are trying to look for is in this scale, smaller than the virus molecule. If in a standard wafer, which is 300 millimeters dimension, we have to verify that in 1 hour and give them all the defects that are available in that wafer. So, and the scale of the problem is huge these days. The standard Apple A15 chip has 15 billion transistors these days. And in a wafer, roughly there would be about 600 chips in there. So it adds up to 8.5 trillion transistors that we are validating and measuring and trying to find multiple tens or maybe hundreds of defects in them. So that adds up to finding like one needle of which is the problem needle out of a trillion needles in a haystack. So that is the scale of the problem that we are trying to handle. And how do we do this? As I said, KLA is a high technology company. It's a multidisciplinary company. There are a lot of physicists, mathematicians, optical engineers, electrical engineers, data scientists. All of them come together, and what we build is a glorified microscope, a lab microscope. All of you are familiar. There would be a platform, a stage on which you put your bacteria sample, and you turn on the light, a light source, and you adjust the lens and optics, and then you start looking at the bacteria sample through your eyes, which is your sensor, and then you see how the bacteria molecule is growing. The human brain is doing the analysis there. That's what is happening in the lab. Similarly, we have a glorified microscope. That's what we are making here. And the small difference is the light source that we are using is 2x the brightness of the surface of the sun. Small difference from the lab microscope. And what we use is a laser pump, laser pump creating a fusion inside the bulb, and we need to make sure the bulb doesn't explode. That's our light source. And the stage on which you place this wafer is a really high-speed, automated, no vibration stage, and it has to be very precise. When it moves at really high speed and it is trying to get you to the point of interest, it needs to stop precisely at that moment, because the dimensions you're measuring is in nanoscale. It has to be a really precise stage. And then the optics that we're using. The optics, it's low aberration optics, and the filters that we are using along with these optics, we have light wavelength varying from a deep ultraviolet from 190 nanometers all the way to 450 nanometers. That's the scale, light bandwidth that we use, light wavelength that we use. And the sensors is a custom built sensor that we have developed on our own, which is capable of generating data at the rate of multiple gigapixels per second. All that fire hose of data is getting into our image and data processing stack. This is the HPC cluster that most of us are familiar with here. And all other subsystems, I'm not comfortable in it. I am not familiar with it. The last subsystem is where I have my background in, and most of the audience here also would have background in, right? This is how it looks like, the product, the final product that we build. This is the latest Gen 5 machine that we have built. If you see the last rack at the bottom, on the back side, with the blower fan on the top, that is where our mini supercomputer is, and we like it so much. So another view of the same machine. So you can see the other rack is on the other side. Multiple racks of a mini supercomputer is built in there. Again, we have to find all these defects Our goal is to try to find the defects in 1 hour per wafer. Let's see. Showing the same thing in a data flow kind of view. This is how it looks like. You get the wafer, you go through the optics, camera, and sensor, and you start getting the wafer images, and then you start processing that on the HPC cluster. It's a standard Linux cluster, the way we build. I heard this is a 40-year-old company. I heard stories that in the past they used to make custom ASICs for doing this processing. I mean, the standard what we do is image processing and vision algorithms. All the tricks that are available in the bags in image processing, that's what we use. Traditional algorithms, not much of machine learning yet. We are making slow inroads into machine learning, but we are heavily traditional image processing algorithms that we use. Primary reason being, for learning algorithms to be successful, we need to be familiar and have a lot of data. Our customers, the way their processes, their materials are changing every day. So they do not have a lot of data which we can leverage on to depend on the learning algorithms. So it's still heavy traditional image processing algorithms, that's what we use. And another major difference between, so before I got into this role, I'm just an year old in KLA. Before I got into this, I was at NSF computational centers and Department of Energy computational centers. The primary difference that I see in how we build Linux clusters here and compared to other centers is these resources need to run in a push button mode. They are like products. They go into fabs. All these fabs are high secure areas without air-gapped environments. Logically, there is no network line going in and out. The fabs do not have the 25-year, 30-year HPC experienced admins and file system admins there. It's primarily operators that are there in the fabs. So these machines, starting from they should just operate on push button mode. As soon as you power on the machine, the master node needs to come up. We use standard net boot. We try to avoid using local drives on all the compute nodes, reduce points of failure, and so master node needs to come up. All the compute nodes need to come up, and we have to instrument these machines heavily for any component failures. We have to build a monitoring infrastructure into that, such that if there are anomalies that are observed in the field, operators quickly know how to resolve them. My 25-year HPC expert who is sitting in the company headquarters do not even have SSH access to all these machines. They are air-gapped machines. So the system should be running on their own. They should be generating enough data, enough logging, such that the field operators can handle them on their own. That's the innovation, that's the challenge that we are handling in this environment. So everything needs to be orchestrated well, and we have to develop enough automation, enough scripting, such that as soon as the button is pressed, the system is just running on its own. Let's see. So here is an example of what the algorithm, the kind of approach that we take to find their defects. So if you take a wafer of 300 millimeters in size, as I said, there would be roughly about 600 chips or 600 dies printed on that wafer. Most of them would be identical, right? Our goal would be to start taking pictures of adjacent dies and comparing them. That's one easy approach, and that's a simple approach that we take, right? This is one of the approaches that we take. Another approach is, as I shown in the previous slide, design and the ground truth information is available to us. We know the actual design that the fabs and they have used when they went through these process steps. So we leverage that and start. The way the optics look and the way this ground truth looks, they do not look identical. We have to continuously align these two together, because as we go through the different layers, the design truth changes. So we have to align that. That's a challenge that we handle. That's another approach on how we find the defects and how we do various measurements that are critical for our customers. Right? And these are some of the factors that we look at. Excuse me. So we talked about finding defects nanoscale. Nanoscale. To find defects at that scale, you need to have really high resolution. High resolution means you have to use very small light bandwidths, so go into deep ultraviolet. If you go to really small bandwidths, small wavelengths, what does that mean? The trade-off there is less penetration. So we cannot have higher penetration at small wavelengths. Whereas if you have an application where we need to penetrate a lot, where the object that you are imaging has much higher depth in it, you need to have more penetration. At that time, what we use is use a higher wavelength, trading off resolution. So these are the challenges that we face, and we try to do a trade-off. In all these environments, there is noise that we would have to handle. So on any surface, any layer on any surface, there would be natural variations, which would manifest as color variation in the optics and the images that we take. So that is all noise which we would have to handle properly. These are some of the challenges that we face. Coming to the kind of data rates that we are seeing, so as I said, there would be roughly about 600 chips, 600 per wafer. And the sensors that we are using these days are capable of generating multiple gigapixels per second of data. And that can add up to roughly 300 terabytes of data per hour. So each wafer, as I said, our goal is to process within an hour, can add up to 300 terabytes of data. Data rate is not heavy compared to many other numbers we have seen in these slides, but data volumes is humongous. It's really, really high. That said, we do not try to save all this data for a period of time. We try to, these machines are run as stream computers where you get a wafer, you scan it, you find the defects, and discard the data for most of the cases. But we are coming up with new algorithms where we do need previous layer defect information, such that as we are finding new defects at a newer layer, we would having that old information is useful. So newer algorithms are demanding storage of this data. Right now we do not store all this data is what I'm saying. And in future, I think the newer algorithms are asking for it. So there is a scope to optimize and innovate heavily in this area. So these are the reasons why we are interested in DDN. A single platform can scale up, starting with a low. You can just have 2 drive chassis or 4 drive chassis, or scale it all the way up to 65 gigabytes a second write performance and 90 gigabytes a second write performance. So this gives us the ability to scale with one platform. As I said, once the system goes into the field, there is very little access for us to do maintenance and enhance it easily. So having to change less things is better for us. So if we start with the building block and we can add on top of it easily, that's a good feature for us. That's something that we look for. And so that is the inspection workflow that I've talked about so far. This slide talks about a special application, a special use case called an offline virtual inspector. So offline virtual inspector is a product that we currently have. It's nothing but just a massive storage device. And this is the next generation of this product is where we have collaborated with DDN and coming up with a solution. Basically, the idea is, within the tool, we do not have a lot of storage where we are not holding all these multiple terabytes of data per wafer. But you can think of having this storage device, external storage device connected to the tool, capture image data from some number of wafers, and then disconnect it from the tool and use that for research and development purposes, where you can play back the information as if it's coming from a real tool, and you can tune the parameters. The width of the sensor, the dimensions of the sensor, the rate at which each of the sensor is grabbing image data. You can tune all of that. It sounds like an obvious application. So this is something that we do right now. And this is the first product wherein we adopted DDN storage. And here is a template. This is a busy slide, but because it's the first modest DDN machine that KLA has adopted. We targeted for 40 gigabytes per second system, modest system. The problem was not architecting this machine or even achieving this number. I think Scott and Andre, if they are here, I have to give a big shout out to them. They put together the config of this machine within days. And once the system is delivered, hardwired and configured, within days we were able to do the tuning and get this number. But the biggest challenge for us is, as I said, these systems go into air-gapped setups where we do not have, our senior administrators do not have access to those machines. So everything has to be properly instrumented such that they can run on their own. And components do fail. I mean, HPC resources, we know hard drives fail, memory DIMMs fail, if CPU fans fail, we would have to swap out. But we need to have a proper monitoring, infrastructure, logging, analysis, everything in place. So collaborating with DDN to get to that state such that the storage subsystem also can run on its own to the extent possible and reduce the single point failure components as much as possible. That is very critical. I know any DDN installation at an NSF center or a DOE center, they will have a DDN support contract, and DDN engineers would get onto the machine and help them resolve issues, and that even KLA senior engineers do not have access to these machines. So DDN engineers will not have access to these machines. All that we're relying is on these log information that gets manually transferred out of the fabs and emailed to us via pictures, via emails. That's the only information that gets to the senior engineers. So we should have everything instrumented in such a way that we can give directive inputs to the field personnel. So, and coming up, DDN was very collaborated with us, and they came up with a new support model for this, a new business model for this. So we highly appreciate that, and yeah, thanks for that. So finally, my final slide, some new challenges that are happening in semiconductor manufacturing process. Some of them I have highlighted. The process complexity is increasing, that multiple hundreds and thousands of steps that I talked about. The operations that they are performing in each of these steps, it's becoming a lot more complex. And the materials they are using are also brand new materials that they are using. So handling all of that is a new challenge that we are facing. So we have to come up with new algorithms to handle that. And a lot of device structures are growing in 3D, three-dimensional. These are nano-scale skyscrapers that are being built, especially in all the memory customers. So being able to inspect and do metrology, do the measurements in that kind of layouts is also a new challenge that we are working towards. I think that's everything that I want to talk about. Finally, thanks to Scott, Andre, and all the DDN engineers who helped us in coming to the stage. Thanks, everyone.